Looking at section 10.3, the Newton-Raphson method, and this is another numerical method. I'm not going to go into the details of exactly what I mean by a numerical method. I've covered this chapter up to here in other videos if you want to go back and watch those, and there are details as to what exactly we mean by numerical methods and things in there. It's not only a numerical method, but it's also an iterative method. It's not the method of iteration, but it's an iterative method where we find an approximation to the root of a function, and then we go through a process and find a better approximation. We go through the same process and we find a better approximation, and so on. Okay, so in other words, we're going to produce a sequence that starts x0, then goes x1, x2, x3, x4, and so on, and that sequence should converge, should get closer and closer to one number, and that number will be the root of the equation. That's the idea here. And the way that we're going to do that is, I think, pretty clever, and it works like this. Here is our function f of x, and here, of course, is the root, okay? And we're going to start with an approximation. Now, the approximation has to be fairly good to start with. If we're miles away from the root, we might have problems. And the first approximation is going to be called x0, and we're going to look at f of x0. Okay, so this point here has coordinates, excuse me, let's just get things out of the way. This point here has coordinates x0, f of x0. Okay, that's that point there. Now what we're going to do then is we're going to look at the gradient, the tangent, sorry, the tangent to this curve at that point. And if you follow the tangent down, the point where that tangent hits the x-axis is closer to the root than we started off, isn't it? So that is going to be x1. And that is the whole method in a nutshell. We're going to go from x0, we're going to go to f of x0. If we drew the tangent and followed it down to where it hits the x-axis, that is a better approximation than we started with. And then we can repeat the process, go back up, follow the tangent down, go back up, follow the tangent down, and we end up with these sort of zigzags that home in very quickly on the root of the equation. So we're going to express that algebraically. Well, this point here is x0, f of x0, and we have the gradient of this tangent here is f dash of x0. Okay, and we've got a method for finding the equation. Excuse me, y minus y1 equals m lots of x minus x1. We've got that formula, haven't we, for finding the equation of a line if we know the gradient and we know a point. So, well, y minus the y coordinate equals m, the gradient of the line, times x minus the x coordinate. There we go. So here is the equation of this line here. And what we're looking for, well, we're looking for the x coordinate where that line crosses the x-axis. Well, that happens when y equals 0. So y equals 0 minus f of x0. And we're calling that x coordinate x1, aren't we? So, in other words, we want to find x1 out of this equation. So if we know x0, if we can rearrange this equation to tell us what x1 is, then we know how to go from x0 to x1, and then we repeat the whole process from x1 to x2 and so on. So we're just going to rearrange this equation a little bit. I'm going to divide by f dash of x on both sides, so f of x0 over f dash of x0 equals x1 minus x0, and then rearrange a little bit more. x1 equals x0 minus this thing. Okay? And that's how we get from x0 to x1. And if we want to do this to go from x1 to x2, we do the same thing, and x2 to x3 and so on. In other words, xn plus 1 is xn minus f of xn divided by f dash of xn. So there is our Newton-Raphson formula, which will be familiar to you if you're revising, and will not be if this is the first time you've seen this topic. So there is the formula, and let's just see it in action in example 6. So example 6 is a fairly typical exam kind of question. Part B and C are absolutely straightforward, standard things. Once you've practiced this, you'll have seen those things lots of times. Part A is checking whether you actually understand this method. So here it goes. The diagram shows a part of the curve with the equation y equals f of x, where this is f of x. The point A with x coordinate p is a stationary point, and the equation of f dash of x has a root alpha in the interval of that. So why is x naught equals p not a suitable starting point? Well, if this is a stationary point, the gradient of the curve, when the x coordinate is p, the gradient of the curve is going to be 0. By definition, it's a stationary point. So if the gradient of the tangent is going to be 0, the tangent is never going to cross the x-axis, so we can't use the Newton-Raphson method. Okay? Or if you like, if you wanted to put that algebraically, if the gradient of the tangent is 0, we'd have to divide by 0 in this formula, and we're not allowed to divide by 0. So, using x2 as a first approximation, which seems a bit of a funny first approximation given that we know that the root is between 1.8 and 1.9, but never mind, they want us to use x equals 2 as a first approximation. What do we get? Well, the derivative of the function is this expression here. So we take x naught equals 2. x1 is given by this. So that is x naught is 2. F of x naught is what we get when we take 2 and we stick it into this equation here. And it turns out that that will churn out a 2. F dash of x naught is what we get when we take x naught and we put it into this equation here. And it turns out that we get a 15 out. So x1 equals 1.86 recurring. Then we take 1.86, we put it into f dash, we put it into f. We take those numbers and we put them in here and here, and then we get x2 equals 1.855 and so on, okay? What I haven't told you so far about the Newton-Raphson method is that there are situations where it won't work, certainly won't work as well as it should, and there are places where you can have problems. We don't need to deal with those as part of the A-level course, but you should be aware of that with all iteration methods. And the way that practically we show that we're aware is that we always check. It looks to me like we're getting 1.856 to 3 decimal places. That seems to be the answer. We need to check that that's the answer. How do we do that? Well, we check 1.8555 and 1.8565, the upper and lower bounds on that number. And we check that there is a sign change in between those two numbers. And if there is a sign change in between those two numbers, then to 3 decimal places, this must be our answer. Okay? So that's Newton-Raphson method. The only thing to say about section 10.4 is that we're going to apply the Newton-Raphson method or the iteration method in context. Everything else is not part of this chapter. If they're asking us to do things about modelling and other things, the mathematics behind those we've studied elsewhere. That doesn't mean you might not want to go through some examples and read this section carefully. It's certainly a section worth practicing. It just means that the point of me trying to do these videos is to show you the maths in each chapter, and there is no new maths in section 10.4. It's just applying things from earlier on in chapter 10 and earlier on in the whole A-level course. So there's chapter 10. Good luck with that.